Okay, number 13 asks you to use a known Taylor form. If you need a known Taylor form, I will give it to you. I do not expect you to have those memorized. Way more important things to put in your brain than Taylor forms for different functions. So cosine of x is equal to, I wrote it down, -1 to the n power x to the 2n factorial, because cosine is an even function. It gets all the even exponents. And we want to write the Taylor series expansion for cosine of the square root of x. So we just plug square root of x in there. So x to the 1/2 to the 2n over 2n factorial, and 1/2 to the 2n x to the n over 2n factorial. Now, we did a lot of practice on these where we plugged other things in, and it was important to divide into pieces. So I want to do a couple more examples, which works out fine because I cut that last video off, and this one will be really short if I don't add something to it. So let's figure out cosine of x plus 3. Then you would do the sum. N goes from 0 to infinity, -1 to the n, x plus 3 to the 2n over 2n factorial. So that's really easy. What if we needed the cosine of 5x instead of just cosine of x? 0, -1, we would have 5x to the 2n, not 2n plus 1, over 2n factorial, which I would really like you, if you had such a thing, to separate into -1 to the n, 5 to the 2n, x to the 2n over 2n factorial, because if perchance you were asked to integrate or differentiate such a thing, separating it into pieces keeps you from mistakenly applying the rule to the 5 as well as to the x. Now, just for one more, to add another bit of confusion, what if you had cosine of 5x plus 10? Ooh, then you would need to do a little bit of factoring, because you would want to write that as 5 times x plus 2. So that would be the sum of n equals 0 to infinity, -1 to the 5 times x plus 2 to the 2n over 2n factorial, which you could divide into pieces. Keep leaving that off. So 5 to the 2n x plus 2 to the 2n, all of that, over 2n factorial. Another trick we used is sometimes you needed to write x plus 1 as x minus minus 1, things like that. Okay. Number 14, we have f of x is equal to 1 over x, and we want to find the Taylor series generated by f at c. So first we just think about Taylor polynomials, because Taylor series are just never-ending Taylor polynomials. And I'm going to write it as x to the -1 power. My center is equal to 2. So I'm going to make myself a little table, And I'm going to take a moment and set up my table, and then we'll meet back here. See if you can get your table set up before you turn it back on. Take a pause. Alrighty, I wrote f of x is x to the minus 1. So the first derivative, -1 falls down, subtract 1 from the exponent. -2 falls down, subtract 1 from the exponent. That was enough for me to see the pattern. I also check when x is equal to 0, it's positive. When x is equal to 1, it's negative. So -1 to the n power when n, is equal to 0 and 1. Then I have n factorial when n is equal to 3. I have 1 times 2 times 3 because 3 exponents have fallen down. I've differentiated 3 times. And then my exponent is -n plus 1. Then I plugged 2 into it. And then I have to remember the form for the Taylor coefficients. Sum n equals 0 to infinity. You have the nth derivative evaluated at your center, so in this case 2 over n factorial times x minus 2 to the n power. So the sum, n goes from 0 to infinity, -1 to the n factorial, 2 to the negative n plus 1, you could put that in the denominator if you wanted to, over n factorial times x minus 2 to the n power, cancel, and just because I can, I think I will put 2 to the n plus 1 power down below with x minus 2 to the n. So there's my Taylor polynomial. Now I'm asked to find the interval of convergence. So just like we found the interval of convergence for number 12, let's use the ratio test. I want you to get started on it and then meet me back. Looks kind of familiar. We did something similar back in problem number 12 when we had x plus 1 to the k over 2 to the k. So now this says that -2 is less than x minus 2 is less than 2. I just multiplied by 2. I add 2 to each side, so 0 is less than x is less than 4. I need to plug in my endpoints and see what happens. So if x is equal to 0, I have the sum of -1 to the n, 2 to the n plus 1 times -2 to the n, which gives me, that's just 1 because I have a negative times a negative, which diverges. And if x is equal to 4, then I have the sum -1 to the n over 2 to the n plus 1 times 4 minus 2 is 2 to the n power, which is the sum of a half. Actually, this would have been a half. And this one would be minus a half. Well, 1/2 times -1 to the n power, but it still diverges. So it diverges on both ends, 0 to 4, because if you look at the limit as n approaches infinity of a half, it's a half. So it diverges by the divergence test. Alrighty, that is Unit 3 stuff. I'm going to call it a day. Tomorrow I'll go through the Unit 4 stuff.